Alright guys, these are the 10.3 notes over applications of vectors. So we're going to be doing a lot of word problems because we are applying things that we've learned to these word problems. But the nice thing is we don't have to learn any new formulas. We're just going to figure out how to use the formulas that we already know to solve these word problems. So, let's see. We've got our formulas. Everything that we're going to need is here at the top of the page. We've got our vector formulas. Remember, this is how to find a horizontal component of a vector. This is how to find a vertical component of a vector. That's why we got v sub x, v sub y. And those lines mean this is how to find magnitude. We've got our right triangle formulas. We've got a squared plus b squared equals c squared. That's the Pythagorean theorem. I know you already know that. Put SOHCAHTOA up there as a reminder. And then we've got the law of cosines, which we learned a while ago, but it's going to come back. This is how you can find a missing side or angle of any triangle. So let's jump right into it. Number 1. Vector A has a magnitude of 5 and points 30 degrees west of south. Vector B has a magnitude of 3 and points 30 degrees east of north. Find A plus B. Okay, let's sketch this. Okay, vector A has a magnitude of 5, 30 degrees west of south. So when you see multiple directions like this, a west and a south, west of south, always start with the second one. So we're going to go south, and then we're going to go 30 degrees towards the west. So here's south, and then I'm going to head towards the west 30 degrees, which means here's where my vector would be with a magnitude of 5. Then I want one with a magnitude of 3 that's 30 degrees east of north. So again, start with the second one. It was north, but then it's moving 30 degrees to the east to give me this vector that is 3 meters long. And it is asking us to add these together. So if I were going to add these together, remember when I add vectors, we go tip to tail. So we're starting with A, and A looks kind of like that, and it's 5. And then it says take B, and we're going to take this vector, and it needs to start where this one ended. So I'm taking this one and moving it right here. So it is starting here where A ended and going about right there. This problem is kind of, it's helpful that these are going in complete opposite directions. So we don't have to calculate any angles. We don't have to do any weird formulas, because really what's happening is we're going 5 meters in one direction and then just doubling back and coming back 3. So remember, our answer is always from where the problem started to where the problem ended, which gives us a measurement of 2, because right, we went 5, came back 3. So our answer is going to be 2 meters. And I see that the direction is the same exact direction as vector A. So it is 2 meters at 30 degrees west of south. That is a fantastic answer, but you might not see that answer on your assignment. So let me give you another possible way to describe this angle. The magnitude is not going to change. The magnitude is still 10. But to find the angle, if we know the vector is headed this direction, we can use this angle to describe that vector. We could also use this angle. The way I would find this angle, well, I know these together make a 90-degree angle. So if this one's 30, this one has to be 60. And this one, I could say, started at west and went south. So we could say 2 meters, 30 degrees west of south, or 2 meters, 60 degrees south of west. Either of those answers would be correct. You won't see both of them on an assignment, but you could see either one. So know that these two are the same exact thing, and either would be correct. Okay, let's try number 2. James ran 15 kilometers to the north, then turned 40 degrees to the right and ran another 20 kilometers. How far is he from where he started? What was his angle of displacement? Okay, this is asking us 2 questions. Let's start with the first one. I want to know how far he got from where he started. So he was running. He's running, and he ran for 15 kilometers. That's a lot of running. Okay. So he went this way, and then he turned. So he's facing this way, and then he turned 40 degrees and kept going for another 20 kilometers. And I want to know, how far is he from where he started? So how far is this? So in order to find this measurement, I'm going to notice that this is a triangle. It's not a right triangle. It'd be a lot easier if it was. It's not a right triangle. So I can't use the Pythagorean theorem, but I can use the law of cosines, which is what I'm going to do. And in order to use the law of cosines, if I want to know this side, I need to know the angle across from that side. And in this case, this angle, I'm going to figure out, because if I know this is 40, I know from here all the way to here would be 180. So I just need to do, oh, come on, don't mess up. I just need to do 180 minus that 40 to get 140. So that angle inside of the triangle is 140 degrees. And then I'm just going to plug things into that law of cosines formula you can see at the top right hand of your page. So C equals the square root of 15 squared plus 20 squared minus 2 times 15 times 20 times the cosine of 140. And let's just put that whole thing in our calculator. Yeah. Let's calculate. There we go. Square root of 15 squared plus 20, oh my goodness, 20 squared minus 2 times 15 times 20 times the cosine of 140. Always make sure you're in degrees. I know that I'm in degrees because I can see in the top right hand corner that DEG means degrees, so I'm good. Make sure you're good. 32.9. So he ended up 32.9 meters away, kilometers away from where he started. That is answer number 1. That is how far he is from where he started. This side is 32.9. This question also asks, what was his angle of displacement? Well, the angle of displacement is how far is that vector from the nearest x-axis? Basically, what is that rotation angle? This, I'm going to call theta. That's what question number 2 is asking. The angle of displacement is this one to the x-axis. In order to figure this out, I'm going to have to figure out this angle here inside of the triangle. And again, I'm going to use the law of cosines to do this. So we're going to have to kind of relabel things, because if this is the angle I'm looking for, if this is angle C, then the side across from angle C has to be side C. It doesn't matter which one's A, it doesn't matter which one is B, but if this is angle C, the one you're looking for, this has to be side C. So be sure you don't get these sides mixed up, because you will not get the correct answer if you do. So let's plug that information into our other law of cosines formula. I'll show you, really, these are the same formula. This one helps you find a side like we just did. This is the one we're about to use to help us find the angle. So it's going to be the cosine inverse of 15 squared plus 32.9 squared minus 20 squared over 2 times 15 times 32.9. Cool, let's put that whole thing in the calculator. Cosine inverse, give me a fraction. 15 squared minus 32.9 squared. Nope, just kidding, it's plus. Minus 20 squared over 2 times 15 times 32.9 gives us 23.2 approximately. So side C That was all for, I'm sorry, angle C is 20, what was it? 23.2. 23.2. That's this angle right here, the one inside the triangle. We just got one more step to get our final answer. If this is the angle that I'm looking for, I know that this whole thing together would be a right angle, right? Since this was due north and we're going to the x-axis. So to find the angle I actually want, I just need to do 90 minus 23.2, which is going to give us our answer, theta equals 66.8 degrees. That is our second answer to this question. Number 3, Jason hit a baseball that flew up at an angle of 54 degrees with a velocity of 73 miles per hour. If the horizontal component of the baseball's vector was 54 miles per hour, what is the vertical component? Okay, so this baseball, whoosh, it went at an angle of 54 degrees at 73 miles per hour. And let's see, the horizontal component was 54 miles per hour. And I want to know, what is the vertical component? So with this one, it actually gave us a lot of information. We've got a lot of options of how to solve this. We know our vector magnitude and our angle, so we could use our vector formula. We could do our 73 sine 54. We could also do some SOHCAHTOA because we have a right triangle. We could also, we've got two sides, we could just do the Pythagorean theorem. Any of those three methods would work and they would all give you the same exact answer. I think I'm just going to do the Pythagorean theorem because that's, the quickest, I think. But whatever you want to do. B equals the square root of 73 squared. Be sure the biggest one, the hypotenuse, is the one that comes first. 73 squared minus 54 squared. Square root of 73 squared minus 54 squared gives us an answer of 49.1. Yeah, 49.1 miles per hour. Cool. Number 4, a toy car rolls down a ramp at 6 meters per second. The horizontal component of its velocity vector was 1.8 meters per second. What was the angle of the ramp above the horizontal? All right, so we got this ramp. We got this toy car. It's going down at 6 meters per second. Horizontal component, 1.8 meters per second. And I want to know the angle of the ramp above the horizontal. That's the theta I'm trying to figure out. Let's see. I know I've got a right triangle. I know I can make a right triangle because if we're talking horizontal and vertical, it's always going to make a right angle. And I want to figure out that angle. So I think I'm going to use some SOHCAHTOA because, again, I have a right triangle. Let's use SOHCAHTOA. I know 6 is the hypotenuse because it's the one across from the right angle. And if this is the angle I'm looking for, this would be the adjacent side. Which means I want to use cosine because cosine is adjacent and hypotenuse. So cosine of theta equals 1.8 over 6. So to get theta, that's going to be the cosine inverse, right? Because anytime you're looking for the angle, you got to do the inverse of 1.8 over 6. Cosine inverse 1.8 over 6, 72.5. Yeah. 72.5 degrees is our answer to number 4. Come on, turn the page. There we go. All right, so here at the top, we've got a little bit of helpful things. First, there's that compass. If you forgot to never eat salty worms or never eat soggy waffles or whatever you learned, there's a compass that helps you remember north, east, south, west, and which one goes where. Something else we need to know is that in the real world, when we're flying planes or driving ships, as one does, the way we describe direction is using either bearings or headings. If you see either of these words, the way we're going to measure angles is different because up to this point, we've always been measuring them from the positive x-axis. Now, we're going to measure them from north. So if you have a bearing of 60 degrees, that means from north, you're going to go clockwise 60 degrees. Right? So bearing or heading always means from north going clockwise. So don't forget that. Don't forget that, excuse me. Okay, let's do number 5. Starting at point A, a ship sails 12 kilometers on a heading of 185 degrees. Okay, let's draw that. I'm going to draw myself some axes, like a little compass, to help me know what the heck I'm doing. Okay, so 185 degrees. So I'm starting at north. There's 90, there's 180, and it went just a little bit more than 180 because it went 185. So it's something like that. It went 12 kilometers at 185 degrees. Then it turns and sails 33 kilometers on a heading of 218. I'm going to redraw a little compass here to help me figure this out. This time I need a heading of 218. So again, I'm starting from north. I know that this vector is somewhere in the middle of it. That does not affect the heading at all. We're starting from north. Excuse me. There's 90. There's 180. And we're not going to make it to 270. We're going to get to 218, which we'll just say somewhere around there. And it went 33 that direction. Now the question is asking, how far did that ship end up from point A? So here's where the ship ended up. Here's point A. That's what we want to figure out. So this setup, I feel like, looks pretty similar to our setup from number 2, where we have a triangle that's not a right triangle. We could use law of cosines, and we could figure out this side. But figuring out this angle is going to be a little bit tricky. We're going to have to remember some rules from geometry with transversals and alternate interior angles. It's going to be a little bit rough. So if you love geometry and you remember those and you can figure that out and want to do the law of cosines, you know what? Go for it. That is fantastic. I'm going to show you another way to do this. I'm going to do this using vector addition. All right? So the way I'm going to add these vectors together, similarly to how we did it when we didn't have pictures, we just had like the numbers, is we are going to add horizontals and we're going to add the verticals. So we're going to get the horizontal component of each one, add them together, the vertical component of each one, add them together. So let's do that. If this one, so remember the way we get our horizontal, if you look at the front of this page, it is magnitude times the cosine of the angle. So this one's going to be 12 cosine 185. And then let's add this one. That one's going to be 33 cosine, what was it, 218? Yeah. That's how we're going to get our horizontals. Remember, vertical is exactly the same, but instead of cosine, we're going to use sine. So 12 sine 185 plus 33 sine 218. I hope you can still see that. Okay, let's put this in the calculator. Let's add those horizontals first. Just go ahead and put the whole horizontal thing in at once. 12 cosine 185 plus 33 cosine 218 negative 40 is what that would round to. And our vertical, same thing but with, oh my gosh, with sine instead of cosine. 12 sine, oh my goodness, 185 plus, these are the right numbers, right? 12, 33, 185, 218. Okay, cool. Just want to make sure I'm not going crazy. Sine 2. Negative 21.4. So what I just figured out is the horizontal and vertical components of my answer. So I know the horizontal that it went, I know the vertical that it went, but I want to know the actual vector, the actual magnitude of my answer. So what I'm going to do is I'm going to plug these into my magnitude formula. So we're going to say that the magnitude is the square root of negative 40 squared plus negative 21.4 squared. As a reminder, when you put these negatives into your calculator to square, you have got to put them in parentheses or it's going to give you an error. Well, I mean, it might give you an error depending on what your numbers are, but it's definitely going to give you the wrong answer or an error. Put those negatives in parentheses. Plus negative 21.4 squared. 45.4. 45.4 kilometers is our answer. An airplane undergoes the following displacements, all at the same altitude. First, it flies 18 kilometers in a direction 20 degrees east of north. Okay, let's see. East of north. So here's north, and we're going to go east of it to give us a vector that is going 18 kilometers east of north. That's west. No, that's not. That's east. Okay, I thought I was going crazy. We're okay. Yeah. Next, it flies 47 kilometers due north. All right, let's go due north. Finally, it flies 60 kilometers, 25 degrees north of west. I'm going to draw myself another compass for reference. We're going 25 degrees north of west. So I'm going to start west. I'm going to head north for 25. 25. And it went that way for 60 kilometers. And I want to know how far it ended up from where it started. All right, well, I know we had the option on number 5 to use the law of cosines. We do not have that option on this one. So let's do the vector addition. That's our only option. So in order to do that, we need to be sure we are measuring our angles consistently. With the problem that we just did above, that wasn't really an issue because it was already given to us consistently because they were all bearings, so it was all from north. This one, we're all over the place. So I need to figure out where they are from. I mean, you can choose anything, but I'm going to choose the nearest, how far they are from the positive x-axis. So like this one would be 80 away from the x-axis because 90 minus 20 is 80. This one is 90. And this one, if I know that this is 25, this whole thing would have been 180. So this piece that I want is 180 minus 25, 155 degrees. Cool. Let's do some vector addition. Let's add our horizontals. Let's add our vectors. So 18 cosine 80 plus 47 cosine 90 plus 60 cosine 155. That's how we're going to get our horizontal, all that put together. And then remember, our vertical is the same exact thing, but it's going to be sine instead of cosine. All right, let's figure this out. I'm not going to remember all those numbers. 18 cosine something 80. Plus y'all get to watch my glitchy board. 47 cosine 90 plus, oh, don't, hold on. There we go. Plus hello, 60, 155. So we got a horizontal component of negative 51.3. Let's do the same thing to get our vertical. Remember, it's exactly the same, but sine instead of cosine. 18 sine 80, close, plus 47 sine 90, plus 60 sine 155. 90.1. Is that right? 1880, 4790. Okay, 90.1. Last step, magnitude formula. Negative 51.3 squared plus 90.1 squared. Come on. Put it in parentheses or you're going to get a crazy answer maybe. 1.3 squared plus 90.1 squared. Since this one's positive, you can put it in parentheses, but you don't have to. You'll get the same answer either way. It's just the negatives you have to be careful of. 103.7. Kilometers. That would be our answer on number 6. Okay, last one. What is the minimum force required to prevent a bowling ball weighing 17 pounds from rolling down a ramp which is inclined 22 degrees from the horizontal? All right, this one's not going to be as bad. You just made it through the hardest one. Congratulations. Let's get this last one done. You got this ramp, right? And this ramp is 22 degrees above the horizontal. At the top of this ramp, you got this pretty pink bowling ball. And that bowling ball really wants to take its 17-pound self rolling down this ramp. And we don't want that to happen. We want to figure out how to stop it from rolling. Well, what is it that is going to make this bowling ball roll? What force would cause it to move down the ramp? Well, that force would be gravity. Gravity is pulling it down, which is going to make it go down this angled ramp. So if I want to keep this ball from rolling, the only force I have to counteract is gravity. So if I can figure out this vertical component, because gravity is vertical, it pulls down, then I'll know how much force I need on this bowling ball. So you got options again on this one. You've got a right triangle, right? If you want to use SOHCAHTOA, you can use SOHCAHTOA. If you want to use your vector formula, you can do that. I think that's what I'm going to do, because I know I have a vector. I know what the magnitude is. I know the angle. So I just want to get the vertical component, and I know my formula for that is the magnitude times the sine of the angle. So to get the vertical component, it's just 17 sine 20. 17 sine 20. 5.8. We need to push on that ball with 5.8 pounds of force, and it will stay at the top of the ramp.